Okay, welcome to Implan's first paper club of 2024. Today I'm presenting, my name is Vahan, and I'm going to present this paper called Mamba, Linear Time Sequence Modeling with Selective State Spaces. I guess linear is the keyword here. Um, the paper is built on top of more other state space models. Specifically, S4 is the more famous one. Um, Basically, those state space models haven't performed well on discrete modalities like language or DNA sequences. And here, authors found a way to keep the high performance of state space models, but make it work well with discrete data. Okay, so there are lots of different tricks here. The paper is actually quite long. It's, I think, 17 pages before appendixes, but they spent a good amount of time explaining things. Uh, so it's a kind of a dual. There is a bit of duality in the sense that the idea seems quite straightforward, but there are lots of technical details that need to be done correctly for the method to work. Right? So I'll try to explain as much as I understood. The paper is not simple at all, but I welcome questions, comments. Okay, let's try to break this down. Okay, so state space models. If anyone has seen those S4, I think there's an S5 now also, sort of models. The idea is that actually, maybe I can find the formula here and start from that. There's a little nice formula here. Look at this formula here. Uh, uh, A and B, for a moment, just think of A and B as training parameters. You have a sequence. XT is the current observed sequence. You have text or you have audio. Those are the sequence values. H is the hidden state. So you have the previous hidden state, and then you calculate the next hidden state. No non-linearity, no uh, LSTM gates, nothing. Right? Very simple recurrent uh, model. So this is the basically linear RNN, if you think about it, if you formulate this way, right? Um, the good thing about this formulation is that um, you can, oh, so many people joining. You can write this formula both as an RNN, but also as a convolution, which will help us, uh, to make efficient training, but also efficient autoregressive generation, right? If you think about transformers, uh, training requires quadratic time, but generation quadratic memory, although flash attention fixes a lot of these problems. But generation is the real problem because autoregressive models, autoregressive transformers require access to all previous observations to predict the next one, right? You can't just look at the last token or the last hidden state and predict the next token, generate the next token. You need access to all previous states, which is why we are limited with a window size, context window, right? When you have a big context window, that's which is the main limitation right now for LLMs, transformer-based LLMs. I think the largest one is now 200K from Claude, but normally you would have like smaller models would have like 4K. If you have more larger, more publicly available models, you can get to 32K and so on, right? But you would never get to like a million. Here, we are able to use a context length of 1 million, and then we'll see why. That's the limitations from transformers, but that's because with a transformer with an attention, uh, you need access to all previous states, right? So when the context window is larger, the multiplication of matrices, the query key value matrices, which you need to calculate for each state, creates quadratic complexity for both time and space for generation. So this is very restrictive. Now, on the other hand, if you have an RNN, right, recurrent neural network, all you need is the last hidden state to generate the next token. So basically, the generation is constant time. Okay, which makes RNNs very efficient for generation. But there is a problem that during training, if you want to backprop, you need to backprop everything, every state back, which becomes very slow, right? That's the classical elements. With LSTMs, things get even more complicated because you have gates and blah, blah, right? Now here, we have a very simple linear formulation. So we learn one matrix A and one matrix B for all states. So this is the invariance part, right? So if they say for the for the state space models, we basically train one matrix, one set of weights for all states, right? Which makes the parameter size smaller. But also because of this and the non-linearities, you can basically keep multiplying. So if you want to uh, if you want to calculate the current state, hidden state, you basically just multiply everything. So if you look at the last bit here, it's like CAAA, this K means K times A and then B. Okay? So B is the other weight. C is another weight. Is the last weight here. So basically, you take the last hidden state, multiply by a matrix, you get the next generated token, right? ABC, and there is also delta, but that's not very important right now. So these are the trainable parameters. Yes, Albert, yes.
So the A and B are supposed to be trained parameters, but then once they're trained, they're globally fixed.
Yes, exactly. Once they are trained, they are fixed.
Thank you.
Which is why you can, a generation, you basically have this C, right? And then you end up actually with one large matrix, which is this K. And then you multiply that by the last hidden state, right? Every time you generate, we have a new hidden state. You multiply by C, and then you get the next token.
Yeah.
Right? There is no need to go back, look at everything. That's the key difference here, right? And then
what is the convolution in 3B?
3B. Yes, so this becomes the convolution, right? The training time, because now you end up with this matrices multiplied, and you have many matrices, and then if you basically open this becomes a convolution operator, which is what you use during training.
Yeah. It's just a little bit hard to sort of see.
Yeah, I know. It's not very trivial at all, but it's funny that during training you treat the same formula as a convolution.
Yeah.
And that during generation, during inference, you treat it as an RNN. That's only possible because two reasons. There is no non-linearity here, because when you do like multiple, so if you have multiple axes, right, you kind of multiply everything with the matrices.
Yeah,
it becomes all linear. And that's the only reason. The other reason is that actually that this A and B do not depend on X. That's the invariance part, right? So what for X, A and B are the same.
And actually, where does the nonlinearity come from? Does it?
Well, if you look at the basic case, there is no linearity.
Say again.
If you look at the basic case, there is no nonlinearity.
Yeah.
So state space models, right? It's just this.
Yes, exactly. But then that's where you would technically lose all the power, right? Because you need nonlinearity.
Exactly, which is why these models don't work well with discrete data like text.
Okay.
They don't work well with text. Yes, Damien?
I was just going to say that so like the state space model can be treated as one of the layers in a larger architecture, so you can still insert non-linearity like activation functions and something like that somewhere else. But this is like the building block of a larger architecture.
Very good point. We can actually scroll down to look at that. Good point here. So this is these are different state space models. because you also have gates, nonlinearities, but this is basically the building block. Right? You also have here projection layers, like linear layers that project to a larger dimension or lower dimension. You also have these other blocks, and then you can put these on top of each other. Right?
Yeah.
Mamba is the current model. Yes, thanks, Damien. But there is no, well, in the standard state space models, there is no nonlinearity inside this little block. Okay.
So it could be just replaced by a by a single linear transformation, right?
Sort of, but then you wouldn't be able to train it like a convolution and then have all.
Yeah.
I guess you could, but then the generation, then you wouldn't have the hidden state. You need the hidden state.
I see.
The last hidden state, right? So at the beginning, they spend a lot of time explaining this trade-off. So the idea is that, let me actually come to the beginning. This is actually a good point, because they discuss here a little bit where it is it? Discretization. We'll talk about discretization. That was a bit difficult. I didn't really understand that part, but there is a part when they speak about compression here, means of compression. So the motivation here is they view this whole thing from the point of compression. Basically, they say if you want a hidden state that is able to capture long context, it must be able to compress this whole information in a relatively low dimensional dense vector, the last hidden state, right? If you make the hidden state small, you make the training more efficient, but you can't save a lot of information there. You make it wide, or if you allow the hidden state to have access to previous points, so it doesn't have to compress much, right? Then you compromise performance, okay?
Yeah.
Which is what transformers do. Here, they say they use this selective selection, so they allow the model to select what information to keep and what to filter out, which is why the hidden state becomes very efficient. So it skips irrelevant parts, right? It learns how to skip the irrelevant parts. That's the main motivation here. How it's done, like there are lots of little technical details here, because once you allow that, the selection, you start breaking all the assumptions. Let's start with the first assumption is, so once you allow the hidden state to choose what information to use and what to filter out, you will have to make this A and B, maybe down here, dependent on the current input. I'm trying to find the formulas. There should be a formula here. I guess here. If you write it, in a more general way, no, it's not here. Let's just go back. I'll just show that original formula and explain that. You basically make this A and B dependent on the current input, because that makes sense, right? This allows you to have different parameters depending on the input, which will allow also to select whether the input is useful or not. The input is the current token, the current X. So that creates a problem, because then you can't formulate this training as a convolution, because these matrix multiplications don't work anymore. Okay. Fortunately, they propose a way, borrowing ideas from here and there, but it's a very noble work. They find a way to keep the training as a recurrent model, but very efficient using GPU structures. So this part I didn't know at all before. So basically, GPUs have two types of memories. So maybe we can go down here and then look at the algorithm, because that's actually the funny part. That's a very important part. Because without that, we are not able to train this effectively. motivations, overview, hardware aware expansion, right? So GPUs have two memories. The high bandwidth memory, this HBM, you can see it here. I think HBM here, and there is SRAM. Now, this is the key of the implementation. They had to implement very low level algorithms because PyTorch is built in RNN training doesn't enable this sort of efficient computation. So they had to actually implement a low level training here. So there is a discretization step. I'll go back to that. But they had to implement the training process. So the discretization and the recurrence is done in the SRAM, which is the more efficient memory, right? And then calculate the final smaller dimensional blocks. So this is, if you look at the original dimensions, this BLDN are the dimensions. Right? The N is missing. Right? You calculate the hidden state, so just the hidden state, which is why the N is missing. Do the serialization, do the recurrence, get the hidden state, and then send it back to the high bandwidth memory. High bandwidth memory is very efficient but small, right? So this is the trick that allows doing the recurrence training very efficiently, right? So in theory, you still don't have linear time. They don't speak about the time complexity, but because you're able to do this in HBM in high bandwidth memory, you don't do the discretization and the recurrence computations. You do this in SRAM, which is why the computations become linear, right? So that's the key part of the training implementation. Any comments? I'm jumping back and forth, but trying to keep the flow. If anything is not clear, just ask. Okay, there's the idea about the training. Let's come back to the formula. I like to look at this formula and then build on from that. So that's here's Damon.
It might be worth just showing quickly the diagram. There's a diagram that shows how the yeah, this one.
This one, yes.
Yeah,
yes.
The GPU SRAM versus HBM.
Yeah, so there's the SRAM, there's the HBM here. So you have the hidden state here from previous time step. A is the training metrics, right? And then you do the green parts are done in HBM. The oranges are done in the SRAM. So you basically do all these discretization, matrix multiplications. These are the multiplications. All of them are done in HBM.
But it's still sequential, right? So you wouldn't, because you need HT in the next iteration.
Mm-hmm.
So you can't. You can just make it faster, but you don't change the complexity of it, no?
Exactly. That's what. Yes, I exactly. So you can't make this efficient like a convolution. So the complexity doesn't change, except that you take advantage of HBM and do these computations there, and then bring it back to SRAM.
I see. Cool.
It's like a engineering trick, similar to flash attention. So flash attention too is also uses GPU structures with clever caching and stuff. That doesn't improve. I don't think it doesn't improve the theoretical complexity, but makes the attention so much faster, right? So these are the sort of tricks that make these models work more efficiently. Okay. Cool. Thanks for those suggestions. So let's. I spoke about the selection mechanism is really a gating mechanism. LSTMs, GRUs, all of them have gates that basically allow the model to either to learn whether a certain input should be used or not. So here there is this selection mechanism. Again, I can scroll a bit lower. show the other algorithm. Here, this one. These are gates. This X is a gate, right? So which allows a skip connection. So basically, here the model learns whether the input should go through this convolution SSM operation or not, right? That's the gating. That's the selection part, which allows to skip to not take into account some inputs, which is important for modalities like audio. We'll see in experiments that this is actually important for things like audio. Okay, let's go back. See what else we have here. I think that's the main thing with the algorithm. There is also this discretization, because the state space models are actually designed for continuous modalities. I'm not entirely sure how this discretization was designed. I don't think it matters too much. Probably it does, but it does matter. But we don't need to understand the details to understand the algorithm, I think. So basically, there is this delta is a learnable parameter also. A is the input matrix, and then there is an explanation at the end. We'll go through them about how each of these parameters makes sense, right?
Yeah. One question. So the delta. So if I understand correctly, 1A is the H prime is a derivative, right? So the delta sort of is the time step going from one time to the next.
Well, it's a learnable parameter. Like those are the parameters, right? Maybe let's scroll down.
Just conceptually, right? So
yeah,
the state model is sort of continuous time, and then you sort of
yes,
chop it up.
So exactly. So if you look at the interpretation of selection mechanisms, they describe all the parameters. Delta is interpretation of delta. Delta controls the balance between how much to focus or ignore the current input xt. So, but A is the ultimately affects the model only through the interaction with delta. Right? So A is just a parameter that is used for discretization, but delta controls how much the xt input is used or not. It's like the gate parameter. B and C, those control the recurrent dynamics, right? If you go up here in the formula, here. So B and C control the recurrence, right? They are the parameters for the current input, but also to get y from the last hidden state.
Yeah.
Delta is not discretization. A is used for discretization. They also mentioned that you can also see them in you can also see A used for discretization, but they don't think it matters.
Yeah, it's like a sort of injection time, right? So when you make your discrete assumption, you sort of assume that in this between time steps, the system is sort of continuously evolving. That's why you have this exponential in there, right? But then after that time, you go to the GPU, use the deeper, or more complex calculation, and then inject it back into the A part, right? So that is, yeah.
There's even inversion here. So
yeah.
this is all done in the HBM.
Yeah, but that is, I think that inversion is more or less just there to make the assumption that X would be applied in 1A throughout the time, right? In order to get that, probably your best guess, because you sort of have to take the eigen dynamics of X out of it, and then apply the rotation of the A matrix to it.
Rotation.
I mean, you can always think, because A is linear, right? So you can sort of.
I see. Yeah.
As a sort of, if X was 0, right? So then then depending on whether A is real or not, but
oh, that's another
you,
thing.
you would sort of expect, right, that the exponential of TA, which in many cases could be like a complex sort of valued thing, essentially just means that your states rotate. If your inner state, say you have a very simple state space where they have only 1 and 0, like two indices, you can create systems that sort of would but you look after it after some time, and you would essentially have the 1 have become the 0 and 0 become the 1, right? And now they have the rotation being dependent on something else, but that something else doesn't apply all the time, but only every couple of time steps. I mean, you could almost think of two time steps, right? You have internal time steps in which you move the HD forward, give it a break, give it a push via this GPU, and then let it rotate a little bit more. And so, of course, it's all rolled up into one, but it's a nice way of thinking about it, I think.
That's a very good observation. I didn't think about that because, but before Mamba, these state space models usually used complex parameters because they worked better, especially for continuous data, right? Maybe then that's when you can see it as a rotation.
Yeah.
Maybe it's worth also.
Otherwise your age would get amplified to some extent, right? So that if there's anything that is non real in the you'd have to refactor A into its eigencomponents, right? But if you have anything that is not purely imaginary, it gets amplified or suppressed up to a point where the leading eigenvector or the set of leading eigenvectors would essentially dominate whatever H is, and so you would get a sort of filtering, right? But you probably don't want that, right? So yeah. But that also means that as long as it's only rotation, you can't gain anything, right? Because you can, in principle, rotate anything back, and you have not gained anything. But by occasionally ingesting the new information, you get something that is sort of non-trivial.
When you rotate, yeah, because it's invariant. You use the same matrix for all inputs. I guess.
Yeah.
Anyway.
Each of the delta A would always be the same, right? And if you
Yeah, exactly. Yeah.
5 times in a row, you could also apply it once with this 5 delta angle, sort of.
Yeah. Yep. Yeah. Cool. But they do actually mention that with this discrete data, after this discretization, they use the real values. Only with audio, I think, complex values perform better.
Yeah. I mean, in the S4 paper, they mentioned, and I think Mamba follows this as well, which is that they initialize the A matrix to the special Hippo matrix.
Oh yes, they do that too. Yes, they do that. They do the same initialization. Yes.
Yeah. So, and I think that sort of starts with complex values, but then they find that real values are better for discrete sequences.
Yeah. Cool. Sounds like a simple idea, but it's actually really hard. So we spoke about linear time invariance part. This basically means that you use the same matrices for all inputs, structure and dimensions. They speak about the dimensions of each matrix. So A square, B and C are vectors. I think that's all. That's all we have here. And then they also talk about the complexity, right? It's not that in that totalitarian states is dimension dn, right? N is the can be represented by n numbers. Is the window size. But this becomes linear in all matrix dimensions. General state space models, we spoke about those. That was the architecture above. So selective state space architectures, those are models similar to what we have here. I guess we don't need to go into too much detail. Hyena is a similar one. It's like a it replaces the S4 layer with an MLP parameterized global convolution. So you kind of add an MLP to the convolution. Or they call it global convolution because it's a convolution on the entire entire context size context window. Let's go down. We spoke about the motivations. Okay, they have actually an interesting example here, which motivates why this selection is useful. So there is this copying task, which standard state-space models solve perfectly, which is, you have these tokens here, and then the task is to copy them exactly into these other points. The key is that those points are equally distant, which means the model is able to learn perfectly well. The linear model is able to learn how to copy this. But as soon as you add spaces between them, model can't learn that because it doesn't know the difference between inputs, right? It only knows positions. But if you say this is a different input to the other, model can't learn that. Okay, so that's the restrictive part. So we talk about these examples because there were other works showing that these sort of tasks are good representations of when transformers work well on language tasks. This is highly correlated with the model. If a model can solve this problem, the selective copying problem, it can also be a good reasoning model as an LLM, right? There is this correlation. And now they say, okay, that's the whole part of the motivation why they add the selective abilities. Okay, and then we'll see later in experiments that actually the Mamba solves this selective copying almost perfectly. Everything else can't do that. Transformers can, but the linear state space models can't. There is a comment here. Oh, thanks, Damien. There is a link to the S4 model in the chat if anyone wants to read that one. Okay. Here we have the two algorithms next to each other. Basically, if you look at the algorithm sequence, the difference is here. The parameters instead of dn are functions now, functions of input x. Okay, all of them, all parameters become functions of input x. But that's fine. So we have this time varying recurrence, which means we can't do convolution, but we have to do scan. Right? Scan is the algorithm we showed before that they use to efficiently calculate recurrence on a GPU. Okay. Okay, so we spoke about this. I don't want to go into too many details about the hardware implementations, but the diagram there should be enough, right? They also talk about simplifying the architecture because basically this H3 and H3 is the Hyena model. So this one has the MLPs. If you look at the square blocks, those are I think those should be MLPs. But here everything is combined, and we have these projections up and down. And there is this nonlinearity for the gating. So if you have gated MLP, it's very simple, right? It's like projection, just a gate here. There is no SSM or anything. Okay? SSM is the state space model. They use SSM for different models. Depending on the context, it means different things, but generally, it's the state space model. Properties of selection mechanisms. So here they motivate the connections to this selection mechanism to gating. I mentioned this before. So basically, gating means you allow the model to skip a certain input, which is the same thing here. There is a theorem that shows that for certain values of parameters, then the selective SSM recurrence takes the form of gating RNN. This is the case, is a gated RNN, right? We have this G or 1 minus G, and then we have this non-linearity with a linear layer. Let's see, this is a gate. Okay. We spoke about interpreting the selection mechanisms. I think this is fine. We spoke about this. Some more details. We spoke about real versus complex parameters, and I mentioned that complex numbers are helpful for continuous modalities like audio and video, but not for discrete ones like text and DNA. Okay. Initializations, Stamen mentioned that they use this hippo theory to initialize. If you're interested, you can read the paper. Parameterization of delta. Nothing too important here. It's fine. Like they give lots of details, like very specific details about how the model was trained, everything really, which is really cool, to be honest. They also call their model S6, but I think they always refer to it as Mamba in the experiments. Empirical evaluations. Let's look at some empirical results. That's probably useful. Okay, so we look at multiple tasks. First, we look at synthetic tasks. These are the selective copying tasks. I mentioned this before. And then we look at language, DNA, and audio. Okay, very thorough experimentation. So, as we said, this task, the copying task, the simple copying task, was originally designed to test the memorization abilities of recurrent models. Right? If the model can memorize which token follows which token, when you copy, you should be able to easily retrieve the next one, right? And then they show here that with the gated architectures like the Hyena or Mamba, those only partially improve performance on selective copying. What is more important is, you can see up here, is adding the S6 layer, right? This is the main layer in Mamba. So whenever you add this, all model performance jumps to almost perfect. If you don't have it, but you have Mamba, but with other bits, there is basically no improvement. Okay. So this is to show that taking into account the input is very important. The other one is this is a really cool plot, I think. Induction heads, right? Models are trained on sequence lengths, different sequence lengths, up to 1 million. Okay, this is a simple task, but as we can see from this plot, as the sequence length grows, all models perform much worse, right? Like at some point they all drop, except for Mamba, which keeps perfect performance for all sequence lengths. So there are no transformers here, by the way. Those are all. Oh wait, no. Rope. This is a transformer, I think. What's MHA? Let's have a quick look. Oh yeah, this is a multi-head attention. So this is actually this is not transformer, but there is an RN. This is an SSM with an attention head thing. So it uses multi-head attention instead of convolution. So there is no transformer in this plot. Let me go back to the plot. Here we are only comparing against state space models, okay? With different position embeddings. So ROP is a position embedding, expose is also a position embedding, okay? So this is still a synthetic task designed to measure modeling interpretability. But it's a good experiment to test how well models scale for long sequences. Before I go to text experiments on text. Any questions, comments here? Okay. So far we see that Mamba outperforms state space models by a huge margin, right? Now let's see if it can compete with transformers. Language modeling, right? That's where transformers shine. Now the first plots here are about perplexity against flops. So lower perplexity is better. So this is like the opposite of likelihood of predicting the next token correctly. Right? If your model is able to calculate the next token correctly, perplexity is lower. Okay, so lower is better. So flops is on the x-axis, and we want to see as we do more operations, like as we have larger models, how does perplexity change? And if you can see, a Mamba performs right on par with transformers, transformer plus class. This is basically the best current transformer architecture. It's like Llama 2, or the other one from Google, but smaller, right? Those are the smaller as in 3 billion parameters. So here, actually 1.3 billion parameters. So those are relatively small transformers, but they match the number of parameters with the number of parameters of Mamba. So it's a fair comparison, right? So perplexity is the pre-training performance. Actually, here, if you look on the second one with larger sequence length, only 8,000, not very large, 8,000, Mamba starts outperforming the transformer, right? A very promising start. Obviously, we should expect Mamba to perform much better on much longer sequence lengths, but we'll see those experiments from DNA later, because those things get really large. Okay, comments here? Okay. Downstream task evaluations, I think it should be here. So they do a very large zero-shot evaluations. These are on downstream tasks, right? So those are all different language metrics. And you have very small models, 130 million parameters, up to the largest one is almost 3 billion, right? And on downstream zero-shot training tasks, zero-shot fine-tuning. Basically, you just give the task without any fine-tuning. So you get those are accuracy numbers. Actually, not accuracy. Each task has its own performance. So for some, this is perplexity. For some, lower is better. For others, like accuracy, higher is better. Bold means best model. And you can see on all of these, Mamba outperforms by a large margin, actually. Like, look at these numbers. It's quite impressive.
I also wanted to mention, I think, if I remember correctly from this paper, the all of the models are not fine-tuned. So these are like just these are the trained models, not fine-tuned towards anything. I don't think.
Yes, zero shot, right? This is it's a zero shot evaluation. Is this what you mean, Damien?
No, I meant like there was no fine tuning. So by zero shot, I think they mean they don't give examples in the prompt.
Yes.
But
you mean fine tune on a specific data set?
Yeah.
Okay, yeah, no, there is no such thing. Oh, they mentioned at the end that it's still we are yet to see if things like fine tuning or discretization, quantization, sorry, and other things that we are used to transformers can be applied on these sort of models. That's at the end in the comments. So we don't probably we can fine tune, because why not? But it hasn't been done yet, right? Cool. So very impressive performance compared to smaller models. You can even see like 7B GPT-J 6B. There is this OPT 7B and so on. So all of these perform slightly worse than Mamba. Right? Even it performs comparably, slightly better often, but comparably, and not always better, sometimes it's a bit worse, but very comparably to transformers that are twice larger. And it's a lot more efficient. Actually, we should look at we look at performance later. But this is the downstream tasks, okay? Now scaling. Obviously, you cannot scale transformers to 1 million context size. Here you can with no problems. That's the cool part, right? They also perform. This is the on the DNA data set, because with DNAs you can get very long sequences. Transformer plus plus again is the current best transformer architecture with rope embeddings, whatever else is in Llama 2. And you can see, so on the left, I think we have the smaller context length, just 1,000. Mamba outperforms slightly, but when you get to massive context length, sequence length, it gets more fixing model size and increasing sequence length while keeping tokens and total training fixed, right? You can see that Mamba basically only improves as sequence length gets larger, right? Which is cool. Everything else even suffers from, for example, Hyena even suffers from increased sequence lengths. Okay? So far, state of the art for this size of models. This is important. Huh? These are 3 billion parameter models, or even 1 billion. 3 billion, no, 3 billion parameter models. Fine-tuning accuracy. So this is actually they do fine-tune. So you can fine-tune on different species of on DNAs from different species, right? And then compute accuracy for, I think it's a classification for species using a DNA. Again, Mamba only gets better with longer sequences, which makes sense, right? And this is a very hard task because 99% or maybe more of the DNAs are shared between those species. So it's very hard to classify because most of DNA is the same, and it's a very long sequence. Right? It's like a million length sequence, like 10 to 20. Okay, and as expected, Mamba gets better as sequence length gets longer because you can look at more information, right? They don't have all models here because, well, you can't scale most of these other models. At least you can't scale transformers to lengths of 1 million sequences. Okay. Questions, or should we look at last one? So the last one is audio pre-training. So this is trained on a YouTube data set. I think it's like a piano concept. You generate piano music collected from YouTube. And again, there is the metric here is called beats per byte. Lower is better. Again, with Mamba gets better with sequence length and outperforms state of the art. Okay. Audio modeling, autoregressive pre-training. We spoke about those. Let's look at this one. What's that? Unconditional generation on a challenging data set of fixed length. Oh, so here I think they compare against GANs and diffusion models. Let's have a look. Autoregressive speech generation. So for speech generation, I think it's this one. They use, I think, some of these. Yeah, waveGAN is a GAN. There is also diffusion model. Those are the state of the arts, right? Very in computationally inefficient models. Both GANs and diffusions, especially diffusions, can be very expensive. And this is a generation of speech clips. Okay, and again, Mamba outperforms state of the art by a significant margin. Look at these numbers. I like this and this. It's quite amazing, right? Again, maybe too good to be true, but I think it's just a new amazing architecture. We are still yet to see how they perform on when the models get larger, because as the model gets larger, they will probably need to do more engineering tricks because GPU memories might become more limited and so on, right? Can you fit 70 billion parameters in SRAM? All these things become more challenging, but this is very promising, at least for now. Also, they report speed and memory benchmarks. I think we can look at this before finishing. So let's look at throughput on the right side here. Throughput, how many tokens per second can be processed, and then with increasing batch size, right? As you can see, at some point, transformers just don't fit anymore because it's too much memory. So the transformer is a 7B model, and they have a 7B Mamba. I think this may be incorrect. I don't know if they had 7B. They had a 3B. The largest model was 2.7B. And then you can see that the smaller Mamba, right, the blue one, is incredibly efficient, and the large one fits in memory. Obviously, the throughput is much less than the small Mamba, but transformers don't fit here anymore, right, out of memory. Similar thing with time. Again, as sequence lengths get longer, at some point, PyTorch's built-in scan doesn't work anymore. The other one is convolution doesn't work anymore at some point. So which is why they had to implement their own efficient scan. Remember, we're using GPU memory structures. Flash attention requires more time as sequence length gets longer, but flash attention 2 is the current state of the art. And we have the Mamba, the current efficient scan, remaining more efficient as batch size increases. Right? Cool. What else?
Yes. On the sizes of Mamba. So you mentioned that they show a 7.9,
6.9. This looks weird, no?
Yeah. So what happened there was that they haven't released the weights for this Mamba model. So the last Mamba model that is open sourced is like 2.8, I believe.
2.7. Yeah.
Yeah, but this one's like the proprietary that they have that they use paper. Yeah.
Oh, nice. I didn't realize it. Of course they do that. Of course you want to keep the best model, right?
Yeah.
But they don't report performance on this model. Oh, interesting. It must be better, right? Or maybe it's not better than Llama 2, so they don't want to report it quite yet. That would be interesting. Okay. I think that's all. Any more comments?
Yeah, I wanted to ask, as I understand here, to Mamba is a selection space mechanism which allows to skip unimportant input. And it works good with like spare data like audio where you have a lot of noise which you can filter out, but it will actually for real data like text, it will work with same speed as or usual algorithms which we know like GPT-4. If you have some article, some scientific article, it has a very low amount of skippable data, and on that article, Mamba and
Can you just give me 1 moment, please? Sorry, Mikola, let me just stop the recording.